So how many of you have dealt with graphs? Right, so a couple of you. How many of you have never dealt with like graphs and I'm not talking about like XY plot graphs. I'm talking about nodes and edges or vertices and edges type of graphs. So none of you so you've never heard the term vertice and edge. That's okay. I just want to make sure that I'm starting out from ground zero for everybody. Okay. So graphs are possibly one of the most useful data structures out there because they describe so many things. Primarily what they describe is things and the relationships between things, okay? The most common graphs are essentially locations, right? I've drawn that on the board before, where basically you have some city, right? Okay? Right, you have some city A and you have some city B, right? And you can travel from, and I have a connection between them, saying you can travel from city A to city B. This is the most common type of graph where basically you're just finding locations between each other. Or at least it was before the rise of social media. Now this is person A, and we have person B, right? And we have person C, and if you have a line between you, you're friends. You're on social media. Okay? Right, so A and B are friends, and B and C are friends, but of course, but A and C of course are not friends. We also have but if you're on Twitter, right, there's in the friends model, there's the following model, right, where somebody subscribed to somebody else's notifications. So we might make that a more directional relationship. So A is subscribed to B, B is subscribed to C, and C subscribes to B. So B and C subscribe to each other. A and C don't subscribe to each other at all, and A subscribes to B, but B does not subscribe to A, right? So graphs are very useful. You can see that basically we went from locations to social interactions that we've mapped here. You can also map the flow of energy or the flow of water with these things. Graphs are extremely powerful data structures because they describe relationships, and humans are about two things: stories and relationships. That's it. That's what we are. We're stories and we're relationships. So, and since a lot of human interactions depend on relationships, and a lot of, this describes a lot. This is a data structure for keeping, track of a lot of human relationships. Similarly, we also can, from an economic standpoint, we care about like relationships between goods and products, and also like how much does it cost to get from A to B, or how much does it cost to get from some abstract state A to some abstract state, as in like a state of being A to a state of being B. How much does that cost, right? So that's kind of useful. Graphs are extremely versatile for mapping stuff. In that regard. So also unique to to show how unique, and also this is going to be a bit of a unique chapter because I'm not actually going to build a graph data structure. It's actually kind of annoying to do. Instead, I'm going to use the opportunity to as a learning experience to show you, given a library, a Java library, how can you use somebody else's Java library, right? So that's actually what I think our assignment is going to be on this Friday. Something that's actually nice and light and kind of easy, which is learning to use a library. Okay, how do you use an external tool? Okay, so we're going to learn about the graph data abstract type, and we're going to learn how to. There's two different ways to implement a graph, depending on how dense the graph is. That means basically what's the relationship to the number of nodes, which are or vertices as they're called when the mathematics people are speaking, and edges, right? The relationship between the connection, the number of people there are, and the number of connections there are. We're also going to learn about breadth first search and depth first search, which you need to know. And the breadth first search is directly related to a queue, and we've done depth first search when we did the maze solving. We used the stack to do that, but you can also use recursion. And then we're going to learn about weighted graphs also, which are basically, again, if we're talking about like the relationship between, if these are cities, right, then the toll to get from A to B, that costs $5, right? Right, that's a cost to get from A to B, right? Whereas to get from B to C, it costs $0, right? You can travel freely between these guys. So that's a weight there. it has a cost. Okay. So trees, but really what graphs are, the other way to look at graphs is that they're an abstraction of trees. Trees, you only have one parent. Here you have as many parents as you want. In fact, we don't really have that parent relationship or children relationship anymore, unless we're like picking up a graph somewhere and dangling it and shaking it out until basically gravity falls and we create a hierarchy. Instead, we basically we use the terminology neighbors. I guess maybe somebody was watching Mr. Rogers that day. But graphs have been studied long before computers were invented. And then they got folded up into computer science. This is really where computer science and mathematics intersect, or intersected. One famous problem, it was the bridge of Königsberg. This is kind of the historical problem in mathematics. Euler solved it in 1736, and it was basically beginning of graph theory, and started topology apparently. So this is in Prussia, which is currently Kaliningrad, Russia, because the borders are ever changing. And this was the map essentially, okay, of the city. Notice that there are 7 bridges and there's these 4 land masses. So you've got this land mass, this land mass, this land mass, and this land mass. So the challenge is, essentially, and this was like things people would do to keep busy. Could you, essentially, let's see, what was it? I want to make sure. Devise a walk that you would basically cross each of these bridges once and only once. So what you would do is you'd cross each of these bridges only once. So you might think, oh, do, and then you realize, oh, I left out that last little guy over there. Euler proved that basically that children for centuries had been wasting their time on this problem, much to the parents' relief. And then they were annoyed he solved it, I guess, because guess what? You can't solve it. Well, it was solved during World War II when a bunch of the bridges got blown up. So I guess that did solve that problem in the Gordian knot kind of solution. But this was essentially, but this map, right, could be rendered into a simplified map, and then we can take this and turn it into a graph, right, where each of these are a landmass and each of these is a node. And notice that this doesn't look anything at all like this, right? Not really. Well, this guy has 5 bridges connecting him, so this is that node, right? So essentially, all we care about are that between the lines is whether the relationships are preserved here. Okay, so you should read up on this problem. But they can so graphs are important because they're pretty much they focus on so much these days. The routing software, that's you're routing a giant graph when you're routing stuff between the internet. Figuring out where stuff goes in a silicon chip, that's graph problem. Large communication networks, graph problem. Figuring out routing for airlines, graph problem. Maps, graph problem. Course prerequisites, making the computer figuring out whether or not you're allowed to take a course and then preventing you from taking the course you really want to. That's a graph problem. So first thing we need to do is define terminology for our graphs. Okay. So a graph is 2 sets. It's a set of nodes and a set of vertices or nodes, which are those circle things, and a set of edges. Edges are the relationships between the nodes and vertices. It's pretty simple. Okay, mathematically we write it in this annoying format, like saying that G is equal to the set of vertices and edges. Okay, so some mathematical notation that's worthwhile to know. So this V is the set of vertices. Okay, capital V is the set of vertices. If I put the absolute value symbol around there, now it's not actually the absolute value symbol of it anymore. Any idea what this is? If V is the set, then what is it? Then what is this? This is yep, it's the size of the set. This is the size of the set. So this is the number of vertices, and this is the number of edges. Right? That's just useful notation to know. Okay. So you can't have an infinite number of edges. And edges have or vertices, and edges have to have corresponding vertices. You can't just have an edge hanging out by itself, describing a relationship between nothing and nothing, right? Okay, so there has to be, each edge has to have, a relationship like this. It is technically possible that things can have relationships with themselves in certain graphs, but we'll ignore that possibility for right now, just for simplicity's sake. Okay. It's also possible that we have a very sad kind of social network that has a bunch of people on it, but nobody's friends with each other because they all hate each other. Okay, so it's possible for either set to be empty, but if you don't have any vertices, then you're not going to have any edges. But it's possible to have some vertices but no edges. Okay, so what we're going to we're going to be dealing with simple graphs here, by the way. Also, simple being that for any pair of vertices, okay? For any pair of vertices, there's only going to be one. They either have an edge or they don't have an edge, okay? So this is a simple graph. Complex graphs have the idea that there are multiple edges. What is an example of this? Travel by land, travel by air, travel by rail or sea, whatever, right? Different modes of transport. That's kind of an example there. We're just going to be dealing with, one relationship. Things are already complicated enough, right? So we typically represent them as vertices as circles, and edges as things that join them. So mathematically, we can define a graph like this: A, B, C, and D, right? We have the nodes, and I'll use the term node and vertice interchangeably here. It's just when you're coming from a networking background, you use the term node a heck of a lot. C, D, E, right? So we've got these nodes in this graph that's being described, okay? So we've got this node in the graph being described. And then we have the edges that describe the relationship. So we've got an edge between A and B. So right now, the order of the edge, the order that the edges appears doesn't matter, in the sense that A or B of A, right now, this is not going to matter for us. So A has a relationship with B, A has a relationship with D, C has a relationship with E, and D has a relationship with E. Okay? This graph that I drew is the same graph that they drew up there on the board, on the projector. Okay? What I've got over here is, I know it doesn't look the same, but it's the same from a mathematical standpoint. How you draw it doesn't matter. But everybody see how I went from drawing from here, from this abstract notation to the thing you drew. It's not that hard, right? It's not hard at all, actually. An edge is represented by two vertices, by the two vertices it's connected by, right? So edge AB, that's the line between A and B. If there's an edge between X and Y, there's a path we say there's a path from X to Y and a path from Y to X. Okay? Again, the physical layout on the graph you draw, and your computer, it does not matter because the computer doesn't really ever draw your graphs for you. We care about drawing graphs because we're visual, and the computer's like beep boop, right? It doesn't care. So here, again, we can use anything we want as vertices. Here we're using numbers. So here we have the vertices 0 through 6, and we have the edges 0, 1, 0, 2. We have all these edges, and you can draw it like this. You could draw it like this. You could draw it some other way. It doesn't matter. These all describe the same exact graph. The mathematical notation here saying there's relationships between 4 and 6, and 4 and 5, and 3 and 4. You've got 4 and 6, 4 and 5, and 3 and 4, and 3 and 5, and 3 and 5 over there. Right? They're the same graph. So, all right. So, we're going to be dealing with essentially graphs are going to look basically different in two ways. They can be weighted or unweighted. We'll get it, and that's basically do we have numbers applied to these. We'll get into that later. And then graphs can either be directed or undirected, right? Essentially, are you following the Facebook friends model, right? Where basically it's a mutual relationship, or are you following the Twitter subscribe model? Basically, where somebody you can subscribe to someone, but they don't have to subscribe to you. I mean, it also works physically. Where can you get from A? It's possible to get from A to B in this example on the screen, and back from B to A. And you can get from B to E, but you can't get from E to B, right? So undirected is basically if you have an edge. This is an undirected graph on the board right now. Basically, if there's something from A to B, it implies there's B to A. And we visually indicate that by drawing no arrows, okay? In a directed graph, we draw arrows to show you can go from this direction to this direction, right? You can follow the arrow. So we call a graph with directed edges a digraph or a directed graph. And if you have undirected edges, we just call you an undirected graph or just a graph, okay? Because we're just the assumption is that you're an undirected graph until you tell me otherwise. If you're a directed graph, you'll go, oh, right, you've got, these relationships might be just one way. So a directed edge, if you need a physical location, if you don't like the relationship model, then you can look at it like a map model. Directed edges are like one-way streets, right? Take a look at 13th Street just right out here. You can only go one way down it, right? You can go from Montgomery, turn on to 13th, and then take it to Diamond, but you can't go from Diamond onto 13th onto Montgomery unless you like hitting a lot of cars along the way, right? We're going to assume we don't want to break any laws. So we represent the directed edges as lines with an arrowhead from one end to another. And directed edges are represented by ordered pairs of vertices, so source-destination pairs. So here we've got a bunch of more edges. We've got B to A. We've got A to B, but we've also got B to A. We have E to A, but notice we don't have A to E, right? Because there's no way to get from A to E directly. Now, technically, there is a path from A to E, right? There's a path you can follow, right? You can go from A to B to E, but there's no edge there, right? And so that makes sense, by the way, that term I use path. A path means you can get from one location to another location, right? So is there anything where we don't have a path from? Well, we don't have a path from C to anywhere, right? C is what we kind of call a sink. Can't really get anywhere from there. So let's look at this graph over here. So this is a weighted graph where we have a number associated with each. Here we have a number associated with each edge. Let's assume for the sake of I don't know what these numbers are. We really don't care. That's outside. Your graph does not. The graph and graph algorithms do not care what these numbers are. What these numbers represent. They are just units. Okay. But we're humans. We need that. So let's assume they're miles. Okay. Philadelphia to Pittsburgh. Does that sound like 320 miles? It certainly did when I drove it. Might be kilometers. No, it takes like 6 hours, right, to get there. So 320 sounds about right. Then from Pittsburgh to Cleveland is 130, and Cleveland to Toledo, 120. So, these are distances essentially. This look like a pretty useful application of the graph. So weighted graphs graphs with weight are intuitively called weighted graphs, right? Remember what I said about computer science people being on the name game? So now I've talked about paths, and then I've got to also talk about what we call cycles. And those are not like the fun kinds of cycles like you get to sit on. Okay. So two vertices are adjacent if there's a edge from it to another. So Philadelphia and Pittsburgh are adjacent on this graph, right? It doesn't feel like they're adjacent, right? If there was a node between Pittsburgh and Philadelphia, they would not be adjacent. But in this graph, they are adjacent. Okay? and that's a big thing. Graphs only can use the information you give it. Okay? Indianapolis is adjacent to Columbus. Chicago is not adjacent to Columbus. So in this case, A is adjacent to D because you can get from D to A. But D is not adjacent to A, and I'm never going to test you on that definition, okay, for that. What I do like to say is that they're neighbors. I rarely use the term adjacent. I like to say they're neighbors. Fort Wayne is the neighbor. Fort Wayne and Chicago are neighbors. Indianapolis and Chicago are neighbors. Right? They're neighbors. A path is where you've got a bunch of adjacent vertices connected together. So if there's a path from Philadelphia to Chicago, right? You drive from Philadelphia to Pittsburgh to Columbus to Indianapolis to Chicago, right? Something I did very recently. So, and this is a simple path, meaning that basically, in the simple path, you only hit any particular node once. Any edge is only hit once. The only exception is that you can have a simple path that ends where it began, right? You can have a path, right, that starts at your house, right, and you walk over and you go on like a mile-long jog, and your path ends at your house, right? And on your jogging path, you're probably not going to jog down any road more than once, right? Right? But you're probably going to want to end at your house, right? Because that's where your stuff is. Right? So it makes sense that a simple path can end at its own self. Right? This is a simple path. This is not a simple path. Right? We've got essentially this kind of question of where do we end? Kind of deal. A cycle is a simple path where basically where only the first and last vertices are the same. So here we've got a cycle from Pittsburgh to Columbus to Toledo to Cleveland. And you need to have at least 3 vertices to be a cycle. You have to have at least 3 vertices to be a cycle. Okay, going from A to B and B to A isn't enough to be a cycle. You have to go to A to B to C to A to be a cycle. So this is what we call. So this is what also. So another term is connected. This is a connected graph, meaning that every node is accessible to any other node. Right? You can get from because of the wonders of the interstate highway system, you can get from anywhere to anywhere. This is a connected graph, but if we remove the edge between 4 and 6, then this is what we call an unconnected graph. Because you can't get from because this is like if these are the Hawaiian Islands. You can't drive from one Hawaiian island to another Hawaiian island, right? But it's still a graph, and those individual islands, you can drive between the locations in them. So a unconnected graph can be made up of what's called connected components. You can kind of break it up into their own mini graphs, in other words. Can also just be, hanging out by himself. So the relationship between graphs and trees is that trees are graphs. A graph that is connected and has no cycles can be, you can say that that's a tree if you just grab one of the nodes and make it the root and just kind of dangle it. So graphs can be used to figure out if one node in the network is connected to all the other ones. You can use it to map out course prerequisites. You can use it to map out relationships on a social network. You can also, and the most common application, the one we're going to study the most, is finding the shortest route from one city to another. Now, interestingly enough, that you can see that's a valuable problem, because finding the shortest route, well, it doesn't, traveling the longer distances means more money, right? But even if even if our units in the weighted graph were cost, again, you can now change the problem to finding the cheapest route, and you can see how that's a problem with a lot of economic incentive to solve it, and to solve it as efficiently as possible. Okay, so interestingly enough, finding the shortest route from one city to another is not necessarily the hardest problem in the world. Finding the most expensive route from one city to another is mind-bogglingly difficult. There's actually really no easier way to do it than comparing all possible routes from A to B. It's what we call an NP complete problem, and we're going to look at a couple of them. NP meaning non-deterministic polynomial, which means that which is a fancy way of saying that we can check your answer. Is that if you give me an answer, if you say you have an answer to my problem, I can check it in a reasonable amount of time, O to the in some kind of O of n to the dth power. But if you want me to solve it, then I have to essentially look at all possible combinations. So it'll take me either n to the nth time to solve it, or n factorial time to solve it, or something like that. So these are graphs. So how do we build graphs, essentially? There's essentially two ways to do it. Java does not provide a graph abstract data type, and neither does Python, believe it or not, right? So we're kind of on our own here to regards. So what we're going to do, rather than going with the slides, is that we are going to use external libraries for our tool. So and I will go ahead and extend you the option that if you want to try the next couple of assignments in Python, you're more than welcome to do so. Because at this point, the problems that we're going to do with graphs doesn't really matter. So if you're going to use Python, you want to use NetworkX as your library of choice for solving graph problems. See, there's a graph. Okay. What we're going to be doing, if you're like me, I'm going to be using Java because that's what this class is taught in. And we'll be doing Jung. Now, this is the old Jung website, and it works, and the library works just fine. Okay, but I did notice that somebody had grabbed it and forked it onto GitHub and cleaned it up a bit. So they're at a different version, 2.1.1, and Jung, the official Jung, is at, it says it's at 2. At 2.0.1. So, but it works just fine. So I'm going to be using the one from the source forge because I've done that. And essentially, you'll want to download it. Okay. And then you're going to want to learn how to use it. Oops, cannot. Oh, still downloading. That's why I can't open it. So it's downloading. Now, of course, I'm not just simply saying here's a library. Good luck. Almost every single library that's worth, if the library comes with no documentation, it's not worth using. So there's two big things over here that you're going to want. So the first is the API, right? That JavaTux stuff. These are all the classes that this provides. More than you need to know about, right? The one you probably care about, though, is the graph interface, right? There's a bunch of graphs. So let's just scroll down to the graph interface, which is implemented by abstract graph, directed sparse graph. So directed, right, we know what that means now. Sparse, that just simply means, that simply determines what our underlying implementation is, right? If it's sparse, we want one implementation. If it's not, we want another one. But graphs, we can add edges. We can add an edge between two different vertices. We can get an edge that's associated with the vertice. Get endpoints, get all the in edges, in other words, all the edges that go into the vertice, get all the edges that go out of the vertices if it's a directed graph. Are these things connected? Does one go to the other? Is successor, is predecessor, right? In other words, is there arrows from these? That's if they're directed. Let's look at an undirected sparse graph, because Oh, there we go. Get neighbors, get in edges, get edges, get, so returns a collection of edges. That's useful, right? So you've got all kind of like methods you would want to use here. But of course, you don't just learn by going through the API because it's huge. You wouldn't know where to start. Instead, you'd go and click on the thing that says tutorial, right? Or how to achieve graph-based Nirvana in Java. So you've got to just download the library, and then you got to import it, and then you typically run their first program to do it. The issue, of course, is you have pretty much no idea how to import the libraries, I guess. So let's go ahead and load up IntelliJ and see how to do that. So I've got to unzip this first, and let's see what we get when we download this. Okay? You get a bunch of jar files. What is a jar file? So let's play acronym darts, I guess. J probably means Java, so R is probably archive, right? Java archive. They're actually just zip files that are dressed up to look like something special. Like open this archive, see it's got folders in it and then if we open and they've got packages in them. If you look at the packages, you'll eventually hit class files, right? Because we just need the class files. We don't need the source files. So, okay. So if you're in a project, right, and this is true for any IDE, you navigate to your so how this works differs based on NetBeans and on Eclipse. With Eclipse, you essentially copy them. You simply copy them to your top level project folder and add them to your build path. For these, I don't know how it works with JGraphs, because guess what? I built this project originally with Eclipse. So let's go ahead and look at making a new project in Eclipse. Sorry, in IntelliJ. So project graphs, finish this window. Okay, so graphs. So we need to be able to use these files. So let's see. Can I import these files? Well, we're using a modern computer, so maybe if I just Control A, Control C. So Control A to select all of them, Control C to copy them, Control V over here. Ooh, yeah, that sounds good. Okay, I think I've done it. All right, let's test it out. New class, graph test. Public graph test. Let's go ahead and see. Public stack void main. Okay, graph. Let's see if it pops up with these things, or do I need to tell it? Nope, it does not know that I want to use these things yet. So let's look at them. Obviously, I might have to look up how to do this a bit later, but add to build paths. Add as a library. There we go. Project library. So select those, add them as libraries, and now I bet I can use them. So graph. There we go. Now it popped up from edus.uci.ics.jung.graph. Graph, and then I need types of vertices and edges. So I'll use strings to represent my vertices. Actually, I'll use integers to represent my vertices and strings to represent my edges. And that's how basically I import these things in IntelliJ. All right. What about in something like Eclipse? Again, the Control-C, Control-V trick really does help a whole lot. Also in NetBeans, you'll just want to drag them into your file. But in Eclipse, let it boot up. It will. You want to, instead of use as a project, you right-click and select Add to Build Path. All right, if I were to import them into this grading thing, I'd copy, I'd paste them over here, and then if I want to add them to my project, I select them all and say build path, add to build path, and now my library knows that I want to use them as things I want to import from. Okay, my IDE wants, I know I want to use them. I don't have NetBeans installed on this computer, so I can't really show how to do that, but it's a very similar process. Except you can, except NetBeans allows you to right-click on your libraries and say add external libraries, and then you can look for them in whatever folder you downloaded them into. Okay, so the last bit of time, I want to go over like what kind of, how does this work? There's a bit more of how these work. When a lot of these, because they were initially mathematical kind of constructs, they did not really care about the implementations, did not use an object-oriented approach, did not even care about abstract data types. They just had nodes and edges and just assumed it would work because it was math. But so we had to come and clean that up. So there's two different types of representations of graphs. So the first is called an adjacency list. Okay, and that means that for each vertice, it's essentially like you'd have a dictionary. Okay, where the key, it's actually easiest to describe it as a dictionary. Okay, or a map, or a hash table, where the key is the vertice, and then the value is the list of adjacent vertices. Okay? So in other words, for this vertice, I can get to all these other vertices. Right? From here, I can get to here. Okay? That's an adjacency list. It's a list for each. So in other words, if I have this graph over here, something that looks like this, A, B, C, and D, right? Then if I've got an adjacency list, it might look like this. A maps to B, a list containing B and C. B maps to C and A. C maps to B, C, and D, or B, A, and D, and D, C. So you see, it's just essentially a list for each node, the list of all the nodes I can get to. Okay? This is good for a sparse graph, meaning that basically that when you're looking at a linear relationship between the number of nodes and edges. So if you've got like a million nodes and a million edges, adjacency lists are pretty good. The other competing thing is an adjacency matrix, which essentially is a table. Okay? It looks like this. Source over here, A, B, C, D, and destination, A, B, C, D. You don't store this portion of it, really. It's just essentially a matrix, right? It's an adjacency matrix. So can you get from A, so we just kind of ignore these for right now. Can you get from A to B? Yes, I'll go ahead and put a 1 there. What about A to C? 1, and a 0 if I can't. Okay? If I can get from, and you can see how this would work for a directed edge too. For a directed graph, you'd have like, if I can get from A to B, I'd put a 1 here, but if I couldn't get from B to A, I would have a 0 here, right? And then we'd fill this up out as normal. I'll review that when we get back. But the last thing I want to mention is, for this thing, is that we've got is that essentially what about weights? Well, for here you'd put you know, the actual value for the weight here, right? You put like, you know, so if the cost was from A to B was 3, you put 3. But for A to D, there's no edge. You wouldn't put 0 there because there are such things as free edges, right? Example, right? If you've got Philadelphia and you've got Trenton, right? And you've got the Benjamin Franklin Bridge, right? Costs 0 to go this way, $5 to go this way, right? It's possible to have different costs there, and for one of them to be free. Okay. So if you don't have a relationship, though, what do you put for A to D? We just put for A to D, instead of putting 0, we put positive infinity in a weighted graph. And I'll go back over this when we get back next week. So, and I might end up giving you a bit more work than you can do before Tuesday. So, but you'll figure it out. I'm sure. I have faith in you guys. But we're going to go. But anyway, once we learn more about these things, then we'll talk about how do we do breadth first search, how do we do depth first search, how do we do, and then the more important algorithms of stuff like Dijkstra's. The end assignment that I normally do. So we've got this week, and then we've got next week. And typically, what I do is like next week is I give my nice little capstone assignment, which is that I give you a security problem. I give you a graph problem, but it's dressed up like a security problem, and it makes it very interesting to solve. All right. So I think that's it for the night, because I think my voice will just give out if I keep talking.